Standard Society of Creation. And we're so very happy to have you here tonight. We really enjoy talking about creation. We meet monthly, the first Thursday night of every month, usually here at Ascension, but we move around a bit too. So let me just give you a few logistics, and then we'll go ahead and get started with our meeting. We'll bring the agenda up. We'll have an opening prayer from Pastor Millius, if he's here.
I'm right here.
Oh, there you are. Our speaker tonight is Dr. Jason Lisle. Following Dr. Lisle's talk, and we'll give him a chance to answer some questions as well. We'll do some announcements about what's coming up over the next few days. And then we'll close with the Lord's Prayer and the hymn, I Love to Tell the Story. So I'd like to introduce to you tonight Dr. Jason Lisle. We're very honored to have him here tonight. He is a graduate, summa cum laude from Ohio Wesleyan University. He had a double major in physics and astronomy and a minor in mathematics. He earned his master's degree right here in Colorado at the University of Colorado, and a PhD, excuse me, in astrophysics at the University of Colorado, so in Boulder, so he's hometown boy. Dr. Lisle specialized in solar astrophysics and has made a number of scientific discoveries regarding the solar system, including the detection of giant cell boundaries using the SOHO spacecraft. He also does theoretical research and has contributed to the field of general relativity. Since completing his research at the University of Colorado, Dr. Lisle began working in full-time apologetics ministry, specializing in the defense of Genesis. He has written a number of articles and books on the topic, and his most well-known book is The Ultimate Proof of Creation, which we have copies on the back table. Dr. Lisle wrote and directed the popular planetarium shows at the Creation Museum, including the Created Cosmos, and he's also served as Director of Research at the Institute for Creation Research. And before we get started, before I bring Dr. Lisle up, Pastor Millius, would you open us with prayer? Thank you.
In some of our churches, since it's a season of Easter, we often begin with the greeting, Alleluia, Christ is risen.
He is risen indeed. Alleluia.
Let us pray. O Lord God, Heavenly Father, we give you thanks this day for the gift of your dear Son, Jesus Christ, through whose death upon the cross we are forgiven of our sins, and through whose resurrection we now stand before you justified through faith in him. Not only have you given to us the gift of your Son, but you granted unto us the revelation of your Son through the clear word of the Scriptures, and we thank you for that. We ask that you would grant us this night your Holy Spirit, that we would learn through that same word of God. Bless Jason, our brother in Christ, as he teaches us, and give us wisdom and discernment as we consider the topic for this evening. Through the same Jesus Christ, your Son, our Lord. Amen. Amen.
Dr. Lisle, would you like to come up?
Well, it's good to be with you this evening, and I've been asked to speak on cosmology, which is kind of a tough topic. So, but I think it's an interesting one, the study of the structure of the universe and how the universe changes over time. And I think in terms of the structure of the universe, I would agree more or less with the observations of my secular colleagues and the conclusions they draw from those observations. When it comes to how the universe began and how the universe came to be the way it is today, I would disagree with my secular colleagues on a number of points. And so I want to share with you some of the problems with the secular or evolutionary model of the origins of the universe, sometimes called the Big Bang model or the standard model. And I want to suggest to you that Christians should reject the standard secular cosmological model. That will be the theme for this evening. I have a number of reasons for this that we'll go through. So when I talk about the standard model, I'm talking about the Big Bang. Just this, also called the standard model because that's what most secular astronomers hold to. There is, by the way, a standard model of particle physics that I happen to think is pretty good. I'm all for that, but I reject the standard cosmological model for a number of reasons. First of all, the standard secular cosmological model is it's not good science. It's not good science. And while that by itself isn't a reason to reject it, because there are things that are true that are not scientific, right? I mean, not all truth claims are evaluated by science, but I think when we go through the list, you'll find that there's not really a good reason to believe in it at all. The standard cosmological model is not compatible with the Bible, and I presume I'm speaking primarily to Christians this evening, and so if you're a Christian, that ought to automatically eliminate the standard cosmological model. If you're not a Christian, you need to become a Christian and then reject the standard cosmological model. Scientific evidence challenges the standard cosmological model, so we'll take a look at some of the problems. Maybe that's what you were anticipating. We will look at some of those. We'll find that there's observational evidence that's consistent with a young universe, one that's much younger than the secular timescale would allow, because it requires 13 billion years. Well, actually, that number just changed, by the way, but anyway, we'll get to that later. And then finally, we'll find that biblical creation is actually the foundation of science. It's what makes science possible. And so if you're going to have confidence in the scientific method, to be logically consistent, you should be a biblical creationist, and therefore you have to reject the standard cosmological model, which is contrary to biblical creation in a number of ways. So to start, I need to sort of summarize what the standard secular cosmological model is. I just kind of want to go through the major steps of it. Now this is simplified for the sake of clarity, but it's, I believe, a very accurate representation of what my secular colleagues would hold to. It's what I learned when I went through the system and so on. So the universe, it starts when it's contained in a point that's called a singularity, and that is the initial stage of the universe. But how the point got there, and that's not often discussed, but in any case, the entire universe is contained in a point, everything, which then expands rapidly like a balloon. And so that initial point, that initial expansion, that's the Big Bang, right? Sometimes the Big Bang is used to refer to the entire model, I'm going to give you 7 steps here. And sometimes it's just referred to that initial explosion, if you will. But I have to tell you, it's not, according to the model, it's not an explosion in a conventional sense. When we think of an explosion, we think of material that has a location in space that then is blasted away from that location into other locations in space. And that's not the kind of explosion that the Big Bang is supposed to be. It's actually not just the matter that's contained in this point, but space is contained in the point. And if that blows your mind, it kind of blows my mind too, but it's not my model. So anyway, so the universe, it's not matter surrounded by empty space, it's matter and space in a point surrounded by nothing. Not even empty space, if that makes any sense. And so it's the entire universe that then begins expanding. So you see the difference. Material expanding into previously existing space is the kind of explosions we think about, but the Big Bang is all the material and space itself contained in a point that then expands rapidly like a balloon. In the balloon analogy, the two-dimensional surface of the balloon is supposed to represent the 3 dimensions of our universe. Okay, and so when the balloon expands, it's not expanding into more balloon, it's just getting bigger. And so our universe is supposed to be like that. You can think of the 3 dimensions of our universe expanding into a 4th unperceived dimension if it helps you to visualize it that way. So those are the first 2 steps. Singularity, and then it just rapidly expands like a balloon. Energy becomes matter then, because you see that initial point contains all the energy of everything that will ever exist in the universe. All the energy is contained in there, but initially it's extremely hot because it's in a very tiny volume. So you have all this energy in a very tiny volume, very dense, and therefore it has a temperature that's essentially infinite at the point of the singularity. And then as it expands, it cools, and then at some point, some of that energy becomes matter. It turns into hydrogen and helium gas. And so energy can do that under the right circumstances, and we'll talk about that a little bit later on. But initially, you can't have matter because it's too hot. Too much energy to have atoms. So eventually, it cools to the point where you can have atoms. And eventually those atoms become neutral atoms. The protons that formed over here collect the electron that formed over there, and they become neutral. And that happens something like 380,000 years after the initial bang. The matter then condenses into stars and galaxies. So that hydrogen and helium gas collects into stars and collects into galaxies. There's some debate about which happens first, but in any case, it's condensing. Gravity is pulling it together, forming stars, which are formed into galaxies. And then the stars then produce the heavier elements. Heavier elements, anything heavier than, say, lithium. The two lightest elements, hydrogen and helium, are made right in the Big Bang, maybe a little bit of lithium, the third lightest element. Those are produced in the Big Bang, according to the model. Nothing else. The heavier atoms can't be produced in the Big Bang. And so my secular colleague said, well, but there are heavier atoms. There are things like oxygen and carbon, things that are heavier than hydrogen. And my secular colleague said those have been made in stars. And not all stars, because most stars can't do that. But it's thought that the most massive stars, these really big blue supergiants, that it's thought that when they run out of hydrogen, as they're fusing hydrogen and helium in their core, that after they run out of that, they begin fusing helium and so on. And eventually they get up to iron. Iron is very stable. It wants to stay iron. And so you can't, it won't release energy when you try to fuse it, but it'll actually absorb energy. And so after iron, they believe the stars actually explode, and the energy in that explosion, in that supernova, and we do observe supernova, stars exploding, the idea is that in the core, it produces these heavier elements very quickly from the other elements up to iron. And that's how responsible for these very heavy elements that we find in trace amounts on Earth, like uranium and things like that. They're much heavier than lead. When the star then explodes, some of those heavier elements get dispersed out into space. And so, and they sometimes will stick together and make little dust grains. And there is dust in space, and so the thinking is that's what formed that. That dust was all produced in supernova and exploding stars. And then some of that dust condenses and forms the seeds for planets. And a lot of times the hydrogen and helium will condense on part of that. And so you get solar systems. We've already got stars, and so now you get things like planets as well. You even have solid planets like Earth. The gas giant, I guess you could have gas giants even before that step, but they'd just be made of hydrogen and helium. Whereas today, gas giants are made of some of the heavier elements too. And then there's a step that is in the future. Step 7. A lot of people think the Big Bang is a story about the past. It is. But it's also a story about the future. In the current thinking, the universe will continue to expand forever and will die what's called a heat death, which is a little bit counterintuitive because it's actually very cold. But you see, as the universe continues to expand, the temperature will continue to drop and drop and drop. And even now, out in space, the temperature is very cold, but we have hot spots, we have stars and things like that. Isn't that nice? And so the idea is eventually those stars will run out of usable energy. And when all the usable energy is used up, the only thing that's left is just thermal radiation, heat. And it's a very low-level radiation, so it's actually quite cold. And in that condition, life will not be possible because there won't be any stars at that point. The only thing that will be left will be black holes and radiation. And if Hawking's right, even the black holes will eventually disintegrate into radiation too. So it's a very bleak future, and one that I would reject. But in any case, so that's basically, in a nutshell, that's the Big Bang. Starts with a point, expands rapidly, it's got very, very hot temperatures. As it cools, becomes matter, but only the three lightest elements, hydrogen, helium, trace amounts of lithium. Everything else is made later in stars. As stars form under gravity, under the collapse of gravity, they make the heavier elements, they explode, release the heavier elements into space, and some of those elements condensed and made the Earth. And so you're all made of star stuff, according to Carl Sagan and others that hold to that view. If you've heard that expression, we're made of stardust, that's where it comes from. It's the Big Bang. So, my first question, to get you to think, is which of these steps are science? In the sense of testable, observable science. Because isn't that what science is all about? It's about observation, it's about experimentation. You know about the scientific method, right? We do an experiment under certain circumstances to test a hypothesis, and we see the results. Well, how many of these steps have been observed or repeated under laboratory conditions? The entire universe contained in a point. Have we ever seen that? No. Now, again, I'm not saying that it's impossible. I'm just saying we haven't demonstrated it scientifically. That's all I'm saying at this point. No one has seen in a laboratory a universe that's contained in a point. It's just not happened. Or any sort of, we never really observed any kind of singularity. We do think there are types of singularities, types of points that exist in the universe. We think the center of a black hole has a type of singularity in it. There's some evidence for that. We haven't really seen one. And there are some problems that we'll see as we go along here. Expanding, have we seen a point expand rapidly? Well, if we haven't seen a point, we haven't seen it expand, so the second step really hasn't We haven't observed that directly. Now, I do think there's some evidence for expansion of the universe. I think that's even suggested in the Bible in passages like Isaiah 40:22. So I think there is some evidence for expansion of the universe. But I'm talking about the idea that it expanded from a point of no size. And I don't see that. I don't see, at no point in laboratory science have we generated the universe and then seen it expand rapidly. We haven't observed it, and we haven't been able to repeat that under laboratory conditions. Have we seen energy become matter? And the answer to that was actually yes. We can do that in a laboratory. So there you go. You can take particles in the CERN super collider and smash them together, and from the energy of that reaction, you'll get new particles. We have seen energy, if it's high enough, if it's very, very high level energy. It's not the kind of thing you're going to get from your light bulb, okay? But in particle collisions where the energy is enormous, you can get new particles out of that. But there's a catch. Because when we do this in the laboratory, every time we get, say, hydrogen, a proton, we also get an antiproton. Interesting. An antiproton is like a proton, but it has the charges are reversed. It's negatively charged. Antimatter. So in the laboratory, whenever we make matter from energy, we get an exactly equal amount of antimatter every single time. Interesting. Problem, because in the Big Bang view, you got to end up with just matter somehow, right? Because the universe doesn't have a lot of antimatter in it, and that's a good thing because antimatter, when it touches ordinary matter, explodes rather violently. And so it's a design feature that God gave the universe, essentially matter only. There's only trace amounts of matter anywhere that are locally generated and almost immediately destroyed by contact with matter. And secondly, I have to point out that just because we can make matter from energy, it doesn't follow that all the matter in the universe was made from energy, right? That's a separate issue, isn't it? Just because something can happen a certain way doesn't mean it has to happen that way. So there's some evidence that that can happen, but there are some issues because the question is, where's the antimatter in the universe? If all the matter in the universe was produced from energy, where's the antimatter? We'll come back to that a little bit later. So I'm going to say that that's partially verified, but not really, because we don't know that the matter that currently exists in the universe was produced from energy. Matter condenses in stars and galaxies. We've not seen that. Now, you will see in newspapers, oh, this is a star-forming region. I have news for you. They have not seen a star form. Okay? What happens when they see these star-forming regions and they see lots of blue stars and blue stars can't last billions of years. They know they're young, they know they're recent, and so they say, well, they must have formed recently. This must therefore be a star-forming region. But my point is, no one has seen a star collapse. No one has seen a gas cloud of hydrogen helium collapse and form a star. It's supposed to take a long time anyway, so it's questionable as to whether or not you could see this. We don't see stars in the process of formation. And they used to claim a while back that they found some that were surrounded by these cocoons of matter, and so they say inside that is a star forming, but you just can't see it because it's surrounded by matter. Well, that's kind of convenient. But the fact is we haven't seen it. Okay? It's not observable science. And we'll see that there's some issues actually with that, with stars forming. Now, I'll be the first to grant that maybe it's possible. Maybe it's possible for a star to form from gas. A star is not a complex organism with all kinds of design features. It's a ball of gas. So, well, maybe that can happen. But my point is we haven't observed it. And so it's not science in an observational sense. Have we seen stars create heavier elements? Have we observed that? We really haven't. We have seen stars explode, but what's really causing that? Is it really due to a runaway fusion process in the core? Maybe, but we haven't observed it, folks. We haven't seen it. It's not something we've demonstrated in laboratory astrophysics. It's not something we've been able to see with the telescope. We have not seen evidence of enrichment of the surrounding region due to an explosion, like a supernova. We haven't observed it. Might be possible, but we haven't observed it. It's not, therefore, observational science. Have we seen dust condense to form planets? Well, we haven't observed that either. And again, the process is supposed to take a long time anyway, depending on which model we follow. But we have seen solar systems that have dust in them. We now have detected planets orbiting other stars, but we have not seen dust in the process of forming a planet. It's not something we've observed scientifically. And obviously, we have not seen the future of the universe because you can't see the future. So. And my point is not to criticize this and say, well, this is definitely wrong because it's not science. My point is just that it's not science, and that's a very a meager point to make. This is not science. It's in the sense of observational science. It's not something that has been tested and repeated in a laboratory. It's not something you can observe with a telescope. You can observe what we actually see in the universe, and you can make up a story as to how it came to be, and that's what this is. It's a story about the past. So that's the point I want to make. It counts as a model, because a model is a schematic description of a system, theory, or phenomenon that accounts for its known or inferred properties and may be used for further study of its characteristics. So a model is a mental construct of how some aspect of the universe works, or maybe how it came to be. And so the Big Bang counts because it does explain why the universe looks the way it looks. It explains why we have heavy elements that were produced in stars. It explains why we have hydrogen helium, well, they were produced in the Big Bang. It explains evidence for expansion because, well, that's, it has some explanatory power. And models do, by their very nature. But the fact is, we could come up with other stories also to account for that, the way the universe is today, right? You come up with your own model. It's pretty easy to come up with a model. You just have to come up with a story about how the universe came to be the way it is today. Frankly, the Greek and Roman myths count as models because they do explain why the universe is the way it is today. I don't think we can say they're right, but nonetheless, they have explanatory power. So how do we distinguish then a good model from a not so good one? I would argue that a good model has two key characteristics. It's relatively simple. The fewer the assumptions, the better the model. And that just makes sense because every time you assume something, you could be wrong. And so the fewer assumptions you make, the better. Simple. Simple as possible. You've heard of Occam's razor, the idea that when you have competing models that explain a system equally well, the simpler model is the one to go with. It's more likely to be along the lines of truth. So, this is a little bit contrary sometimes to the way laymen think, because they think, well, if there's lots of equations and it's very complex, that's a good model. It's actually the opposite. Newton's laws are great examples of a good model because they can be written down on a note card and they can predict basically everything. That's a good model. Makes many specific and correct predictions. Obviously, if it's making wrong predictions, that's not a very good model. It needs to make correct predictions. And it's not good enough for it to make one correct prediction, right? Even a blind squirrel gets an acorn every now and then, right? So it has to make many specific correct predictions. They do have to be specific. It's not good enough to say, well, according to my model, something will happen tomorrow. Well, and then lo and behold, something happens. See, there's evidence for my model. No, that's not a specific prediction. Now, on the other hand, if I said, at exactly 12 o'clock tomorrow, Mike Rodebacker will be struck by lightning. Now, if that happened, you'd be impressed that I could make that prediction. And Mike would be very sad, unfortunately. But you see, that's a specific prediction, isn't it? And a good model needs to make lots of those. And so let me give you some examples of a good model. A good model is the heliocentric model of the solar system. Another good model is Newton's laws of gravity and motion. Those are examples of good models because they make many specific correct predictions and they're relatively simple. Let me just start with Newton's laws. Newton's laws of gravity and motion. Newton's 3 laws of motion, Newton's 1 law of gravity. You can write those down on a note card. And from them you can predict the motion of the planets centuries into the future correctly, very specifically. You can calculate where the planets will be. That's awesome. Based on 4 little formulas. That's pretty neat. That's an example of good predictive science. In fact, the planet Neptune. Do you know the story of the discovery of the planet Neptune? The planet Uranus, when it was discovered by William Herschel back in the day, and astronomers were monitoring its orbit, they found that it was a bit off from where it should be. And they knew that planets don't just orbit just the sun, they influence each other as well. But they had taken into consideration the mass of Jupiter and Saturn and how that can affect the orbit of Uranus. And of course, Earth doesn't make hardly any difference at all because it's tiny and far away. But nonetheless, they found out the planet Uranus was off from where it should be based on the positions of the planets. And they said, you know what, there must be another planet out there pulling on it. And 2 mathematicians independently worked out the calculation and said, we think there's got to be another planet right here. So if you point your telescope at these coordinates, you will see an as yet undiscovered planet. That's awesome. Think of how bold that prediction is. And Leverrier had the advantage because he nailed in his prediction to, I think it was the Berlin Observatory, and they had good star charts for that section of the sky. And that very evening, they pointed the telescope right there, and they could see a new object there that wasn't on their star charts because it was moving as a planet. The planet Neptune was discovered by math. Leverrier said to be the man who discovered a planet with the point of his pen. That's awesome. That's good science. Very simple, but makes very specific predictions. And that is a specific prediction, right? You look at these coordinates, you'll find a new planet. That's bold, because most places you look, you won't find the new planet, right? You just pick the spot randomly. The heliocentric solar system is not the only model of the solar system. There was the older geocentric model that had the planets going around the Earth. And Ptolemy really worked on that. Ptolemy was a 1st century Greek astronomer, and he had a model where he could get the planet, he could predict the positions of the planets. And I think this is interesting, because Ptolemy's model actually works fairly well. He could actually predict successfully the positions of the planets, make correct specific predictions, roughly, okay? And pretty consistently. And it was used for over 1,000 years because it was so successful. But it was horribly complicated, because in order to make it work, he had to make the planets orbit around nothing in these little circles, while they then orbited around the Earth. And for some strange reason, Mercury and Venus were always aligned with the Sun. They orbited at the same overall rate as the Sun while they did the little circle. The little circles are epicycles. The big circles are different. And then and Mars and the outer planets would always keep the orbit and the epicycle the same as the Sun's. Very strange. He couldn't explain why that was. It just seemed to work. And by adding epicycles, and eventually you had to add epicycles on the epicycles to get it to work really right. But it does work. Even though it's wrong, it works. That's kind of interesting. And then Copernicus comes along and revives the heliocentric solar system. And with that, you don't need epicycles, because if the planets orbit the Sun directly, then when we pass them, that's when it looks like the outer planet seems to back up instead of an epicycle. The interesting thing is that even Copernicus' model is not quite right, because he assumed that the orbits are perfect circles, and they're not. It would take another creation scientist, Kepler, who came along and realized the orbits are elliptical, and that accounts for that. But Copernicus' model is simpler than Ptolemy's, but they both made successful predictions. I think that's interesting. So it's just an Occam's razor that Copernicus wins out. And ultimately, with the advent of modern technology, we can confirm the Copernican model, because in the Ptolemaic model, Venus would never be on the far side of the Sun. And we can confirm that, yes, it does sometimes be on the far side of the Sun, so we can confirm that today. But that's an example of a good model, relatively simple and makes many specific predictions. So how does the Big Bang stack up? Is the standard cosmological model relatively simple? Well, I simplified it to give you the 7 steps, and it may sound like it, but really the recent versions of the Big Bang are pretty complex. And they have a lot of arbitrary assumptions built into them, which we'll cover some of these, that are required in order to make the model compatible with observations. I can't tell you how many times astronomers have observed something that's just not quite consistent with the Big Bang, and they have to adjust the model a little bit. And it reminds me very much of the way Ptolemy would add epicycles to make the model fit the observations. And that might suggest that, well, maybe your model is just wrong and you need to consider something else. It's not very simple. And does it make many correct specific predictions? Well, it really doesn't. And the only one that I can think of that Big Bangers often claim is the discovery of the cosmic microwave background. And this requires a little bit of explanation. If you could see microwaves, you'd go outside at night and the sky would be sort of glowing faintly with microwaves coming from all directions in space. Doesn't matter where you look. And this is thought to be from an enormous distance. We don't really know what the distance of it is, but it's thought to be beyond the farthest galaxies. And so the idea is that very distant space is emitting, for some reason, microwaves. Interesting. And this was discovered in 1964. Penzias and Wilson, they were working on a different project, actually. They detected this hum that's coming from space, and they found there's microwaves coming from all directions in space. And at that point, folks who supported the Big Bang model said, well, that makes sense, because you see, when the universe was really small and really hot, it would have given off a lot of electromagnetic radiation, and it'd probably be kind of in the infrared or visible light range. But then as the universe expanded, that stretches out the wavelengths of light all the way down to microwaves. And so if the Big Bang's true, you'd expect to see microwaves coming from all directions in space, and there they are. So it's a successful prediction of the Big Bang. Well, the interesting thing is, there were actually a number of different predictions. Some people predicted, they didn't really predict microwaves, but they did predict the universe would have sort of an average temperature, and it depended on the model. Some of them said it should be 1 degree above absolute zero, some of them said it should be 50 degrees above absolute zero. So there were a number of different models that made different predictions that were within the standard model, different versions of it. And the one that won out was the one that got pretty close to 3 degrees above absolute zero, because in fact these microwaves have a temperature corresponding to 2.7 degrees above absolute zero. So they're very cold. And that was hailed as a successful prediction of the Big Bang, mainly because the alternative model, which was the steady state model, steady state folks believe the universe had always been expanding and new matter forms to fill in the voids, and that the universe is eternal in that model. And they hadn't predicted a Big Bang. They didn't realize that the universe should have an average temperature. So this has been considered a successful prediction of the Big Bang, but as you can see, it's not very specific, because in fact the range of predicted temperatures was between 1 and 50. And the other thing I need to tell you is that any universe eventually will emit microwaves. Because you see, according to our understanding of the laws of thermodynamics, anything that has a positive temperature must radiate electromagnetic radiation. And again, according to the laws of thermodynamics, everything must have a temperature. And so basically everything has to glow. Everything, you're all glowing right now, actually. It's just you're mostly in the infrared, so you can't see it. The only reason we can see is because of the reflected light from the lamps. But you're giving off electromagnetic radiation because you have temperature. Hopefully 98.6. If you're not, don't shake hands with me. You get the idea. And so my point is, any universe that has sort of an average temperature will give off microwaves. So it's not a very robust prediction. It's just they didn't realize that at the time. But now we realize that. We realize, well, yeah, of course it's going to have microwaves. It would have to. So it doesn't matter whether it started in the Big Bang or whether it started any other way. It's going to have microwaves in it because it has an average temperature. So in any case, you want to call that a great prediction, okay, but it's not very specific, and it's only one, because I can't think of any other real specific predictions that the Big Bang has made where it's been right. I've seen many where it's been wrong, including one very recently where they re-estimated the Hubble constant, and there's a discrepancy between their earlier estimate. It's fascinating. So does the Big Bang really count as a good scientific model? I say no, because it's not very simple, and it really doesn't make many correct specific predictions, and none of the steps of it have been verified scientifically. So I would say that the standard cosmological model is really not good science. It's not compatible with the Bible, and so that ought to give us a reason to reject it right there. Let me show you some of the differences between what the standard cosmological model teaches, what the Bible teaches regarding the cause of the universe. In the standard cosmological model, there's actually not a lot of agreement on what caused the singularity to come into existence in the first place. Some would say it's a quantum fluctuation, but that requires the universe to already exist. And so folks who take that position have to believe we live in a multiverse, and if there's other universes that are straying from one of these multiverses, that just pushes the problem back. It came from nothing, and that's a causality problem, because cause and effect, right? Nothing comes from nothing. That doesn't make it doesn't make sense for the universe to come from nothing. And, it would be ridiculous to approach science with that philosophy, that there's no cause, right? Can you imagine that? If some scientist is going to experiment and he sees this interesting reaction, what caused that? He says, well, probably nothing. Nothing to see here. Some are honest and say, well, we can't know what caused the singularity. That's an honest answer. It's not a very good one. God is certainly sufficient to cause the universe. He's all-powerful, and so some people reject that God a priori. Well, I don't want to believe in that God. Well, that's your problem. But the fact is, it makes logical sense for an almighty God to be able to create the universe. Regarding the time scale, we can't just shove this under the rug, because according to the standard cosmological model, it's 13.8 billion years, or if the latest measurements right, that will reduce it to somewhere between 12.5 and 13 billion years. So that number changes a bit. The Bible indicates thousands of years, because the Bible teaches that God created in 6 days, and it's clear from context those are ordinary, approximately 24-hour days, right? Earth rotations, because each one is bound by evening and morning, and you add up the ages, and so you get so-and-so, and you find us a few thousand years ago. So it's a huge difference, and we can't just sweep that under the rug. It's enormous. The order of events is different. A lot of people think that if you just made the days long periods of time, that would allow the Bible to be compatible with the standard secular model. It doesn't, because according to the standard cosmological model, stars existed long before the Earth, and they have to, right? Because remember the heavy stuff that the Earth's made of, oxygen, carbon, those heavier elements, are supposedly produced in the cores of stars. are made of stardust. But according to the Bible, Earth's made on day 1. Stars are made on day 4. Yes, so the order's different. And if you follow the naturalistic history out, you'll find that the secularists teach that fish evolved long before fruit trees. But according to the Bible, fruit trees are made on day 3, fish are made on day 5. The order's different. According to the secularists, dinosaurs existed before birds. Some of them evolved into birds, right? But according to the Bible, birds are made on day 5, dinosaurs are made on day 6. The order's different. So making the day, stretching out the days doesn't help you. So again, the order of events is very, very different. The future. The Big Bang's not just a story about the past, it's a story about the future, and we've seen that it predicts a heat death, that the universe will eventually lose all of its usable energy, and there will be no life possible at that point. Very sad. The Bible teaches a judgment and restoration. There will be heat destruction, and then there will be restoration, and there will be paradise lost, there will be paradise restored. It's interesting to keep that in mind, because a lot of Christians get, I think, intimidated, because there's some brilliant people that believe in the Big Bang, and I agree with that. There's brilliant people. That doesn't make them right, but nonetheless, they're very smart, and they say, yeah, this is the model we're going to go with. And Christians say, well, yeah, I'm going to be a Christian, I want to believe the Bible, but maybe Genesis not so literal. And then the interesting thing is, though, then they reject the future of the Big Bang. They say, oh, no, I believe that the Lord's coming back. But you see, the Big Bang doesn't predict that. Interesting. ETs, what about extraterrestrial life? And the standard secular cosmological model, life's just an accident in their view. It's where chemistry happens to be right, and hey, it's a big universe, so life evolved here, probably evolved elsewhere. ETs are likely. My secular colleagues, most of them expect to find life out in space. And I'll grant the Bible doesn't say there's not, but I do believe that the most consistent view of Scripture would be that the earth is unique in terms of life. God formed it to be inhabited, according to Isaiah 45:18. The heavens were designed to be for signs, seasons, days, and years, to give glory to God, but not to house life. Earth really is very special. And again, it's made on day 1. All the other objects, all the other planets would be made on day 4, because the Hebrew word for star, Kochav, would include planets as well. So I think we're not going to find life out in space. And I guess I wouldn't have a huge problem if they found moss or something like that out there. But even that I don't expect. And you have huge theological issues to deal with if you have Vulcans and Klingons out there, because they can't be saved. They're not related to Jesus. And remember, it's because we're all of one blood that Jesus is able to pay for our sins on the cross. His blood counts for us because we're related to him. Biblical theme, kinsman redeemer. Lieutenant Worf, out of luck, because he's a Klingon and he's not related to Jesus and he can't be saved. So there's some theological issues there they have to come through. According to the standard cosmological model, the Earth starts as a molten blob that's accumulated from these dust elements as they collect, and then the last ones impact rather violently. Very hot. There's no ocean originally. According to the Bible, it's created as a paradise. Originally created as water. Whereas according to the standard cosmological model, it's rock first, and then the oceans don't form until like 1.5 billion years later. Whereas according to the Bible, the earth starts as ocean, and then the land is made after that, and it's paradise within 6 days. So it really isn't compatible with the Bible. I hope you get that. And there are other things we could point out, but I think that's enough. And to say that it's not really consistent with Scripture, that's not its point. The Big Bang is designed to be a naturalistic explanation for how the universe came to be the way it is today. Now, the inventor of the Big Bang did believe in God, but he held to what's called methodological naturalism. He believed that you shouldn't invoke God when you're doing science. You should pretend that God doesn't exist when you're doing science. And so I reject that view, but that's why he tried to explain the origin of the universe without invoking God. And he got upset when some people said, well, does this indicate God? He said, well, no, you can't say that. That's a faith issue. He believed that those were separate. There's scientific evidence that challenges the standard cosmological model. I'm going to share with you some of these. And I'm only going to share ones that have appeared in the secular literature. Some of them, they'd say, well, we've solved these now, but I don't know that they really have. And others are unsolved even at this time. So these are some scientific problems with the standard cosmological model. One of them is called the flatness problem. And this has to do with the fact that the expansion rate of the universe is very finely balanced against gravity. Expansion tends to make the universe bigger. Gravity wants to halt that expansion and bring it back, right? Because gravity is an attractive force. And so the fact is those two are very finely balanced. And the problem with that is if you run the equation backwards, in the past they have to be even more finely balanced to the point that they're ridiculously balanced at the point of the Big Bang. And so it's an example of a fine-tuning problem. These two parameters, which could be anything in a chance universe, expansion rate and gravity, why are they so precisely balanced? That's an issue. It might not be an issue if you believe in a theistic version of the Big Bang. You can say, well, God orchestrated it that way. But I've already shown you that's not compatible with Scripture anyway. I do think it's a big problem for an atheistic view, where these two numbers just have to work out perfectly. That's the flatness problem. We have the horizon problem. This is kind of interesting because it's a light travel time problem. And that's interesting because a lot of my secular colleagues say, well, if you believe in biblical creation, the biblical time scale of thousands of years, how do you explain distant starlight? How do we get light from those galaxies that are billions of light years away to Earth within 6,000 years? And a lot of times what they don't mention is they have the same type of problem. And I think we actually have a solution to ours, and I don't think we have a solution to theirs. So it's interesting. It's actually, an example of what's the pot calling the kettle black, right? So the way it works, the universe in the Big Bang, remember, it starts out as a point and then it rapidly expands. And so at a certain point, it's like the size of a golf ball, for example. And in that state, it's going to be extremely hot, but some places are going to be hotter than others due to the Heisenberg uncertainty principle. I won't go into details. It's going to have hot spots and cold spots. Even the cold spots are hot, but they're cooler than the hot spots, if you see what I'm saying. So you got hot spots and cold spots. And then the universe expands rapidly. Now these spots are on opposite sides of the visible universe, because we can only see so far, okay? And yet today they have the same temperature, to within a very small margin. Interesting. Well, why is that not still hot and that one not still cold? How did they come to the same temperature? Obviously, they had to exchange energy. If you put an ice cube in your hot coffee, you'll end up with lukewarm coffee eventually, right? Because the ice cube will heat up and melt, the coffee will cool down. That's the nature of energy. Energy tends to go from a hot place to a cold place, naturally, okay? So, you'd say, well, that's the solution then. The hot spot dumped some of its energy to the cold spot. But the problem is this. Those things are on opposite sides of the universe now. And if you do the math, there's not been enough time for light to travel from the hot spot to the cold spot even once, let alone the multiple times it would take to really equilibrate the temperatures. It's a light travel problem. The light has to have gone from A to B to dump the energy there, and yet it hasn't had enough time because it's just now getting here, right? Because we can just now see it. And it turns out making the universe, you might say, well, we'll make the universe even older, and we'll give it more time to. That doesn't work because then those points expand even further away, you see? And so it's not a simple solution. And I'll tell you about what they proposed as a solution for this, but it's a light travel time problem, a horizon problem. And then there's the monopole problem. Physics predicts that there could exist particles that have a single magnetic pole. Like, you play with a magnet and they have a north pole and a south pole. Theoretically, you could have a particle that has just a north pole. That'd be kind of interesting. And those should be produced at the extremely high temperatures associated with the Big Bang, but we don't find them anywhere. Now, we find particles with only one electric charge, but that's different. You can have an electron, which is just negative, or a proton, which is just positive, right? Theoretically, you can have magnetic particles that are the same way. They have just a north or just a south, but we don't find them. They should be produced in the high temperatures associated with the Big Bang. We don't find them, which to me suggests that there wasn't a Big Bang. The temperatures were never hot enough to produce such particles. So that's the monopole problem. Now, these three problems, the flatness problem, the horizon problem, and the monopole problem, my secular colleagues have attempted to solve all three of them with what they call inflation. If you've heard of the idea of inflationary cosmology, that's what it's designed to solve. And the idea is, with inflation, the universe, when it starts expanding, it's expanding at what we might call the slow rate, even though it's actually very fast. It's slow compared to what comes next. Then for some reason, it picks up speed and expands very, very rapidly. That's inflation. And then that turns off and it goes back to the slower rate. Now again, all three states are fast. It's just the inflation is much faster than the one before it and after it. And the idea is that could reduce the flatness problem. It could, because when you do that, it tends to make the gravity and the expansion rate balance a little better. It could reduce the horizon problem, maybe even eliminate it, because the light could get from the hot spots to the cold spots before the inflation phase, and then it gets spread out. And so they're already equilibrated. That might work. And it could push the monopoles so far apart that we never detect one. And so it might potentially solve those problems. But there's a problem with inflation. It really is a story without supporting evidence. They've invented one problem to explain away other ones, and it has problems of its own. What would start the expansion? Some kind of symmetry breaking in physics, maybe. How to turn it off in a graceful fashion. That's called the graceful exit problem. So once you get this universe expanding rapidly, what causes it to suddenly switch off everywhere at the same time? I mean, that's a coordinated effort, right? Okay, so, okay, everybody get ready, okay, and stop. And somehow it stops everywhere. So they've potentially solved 3 problems by adding another set of problems. And so that's not really very good science. There are more problems with the Standard Model, though, that would not be solved even if inflation were true. So these are ones that even if inflation were correct, you still wouldn't solve it. One we might call the singularity problem. There's really 3 problems. First of all, the existence of a singularity. Although that doesn't necessarily prove that you're wrong. Usually, if you're doing like a mathematical calculation and you get infinity as the answer, or you get an infinite amount of mass and 0 volume, that suggests you probably made a mistake somewhere. So it sort of hints that we might have a problem. I'm not saying that the universe disallows singularities, but and by the way, the Big Bang singularity is of a different type than the singularities we think are in black holes, because black holes are surrounded by empty space. Okay, and they have a point of no return called the event horizon. If you fall into the event horizon of a black hole, you're going to die because you can't ever leave. And so anything that's within that distance eventually collides with the black hole. So black holes are clothed; their singularity is clothed by an event horizon, whereas the Big Bang singularity is said to be a naked singularity because it's not clothed by an event horizon. And in fact, there's actually the cosmic censorship hypothesis that says that naked singularities can't exist. And for some reason, they just exempt the Big Bang for that one because it would violate it. But anyway, the second problem is a breakdown of known physics. We have a branch of physics that describes what happens in extremely intense gravitational fields, like associated with the black hole. And that field is called general relativity. That's what Einstein contributed very heavily to. He's built his baby. And we have a field of physics that describes what happens in very small spaces, smaller than atoms, which we call quantum mechanics. However, we have no known physics that can explain what happens when you have both an enormous gravitational field and also a very small space. Because it turns out that general relativity and quantum mechanics are not entirely compatible. They each work in their own realm, but when you try to combine the realms and have a very strong gravitational force in a very small space, smaller than an atom, we have no physics that can describe what happens in that situation. It's not yet been discovered. And that's interesting because that is exactly the situation that the Big Bang is supposed to have started in. Isn't that interesting? So my point is, current science cannot explain whether such a situation is even possible, let alone what happens in it. And so those who hold to the secular model must take it on blind faith that such a thing is even possible. We do not have science that can describe what happens in that situation. And then finally, the actual cause of the singularity. How did it get there and why did it expand? It's interesting. One thing the Big Bang does not explain is the origin of the universe. It's just a story about what happens afterwards, supposedly. But it doesn't explain how the singularity got there and why it expanded. There are guesses, and one of those involve the multiverse idea, which is, by definition, not science, because you can't observe another universe. Anything you observe has to be within this universe. Otherwise, you couldn't observe it. There's the baryon number problem, or baryon asymmetry problem. This is my favorite because I think it's very easy to understand. And so if you were to memorize one of these, I'd pick this one. And this has to do with what I talked about earlier, the fact that all the matter in the universe is supposed to have been produced from energy in the Big Bang. And we can replicate that in the laboratory. We can make matter from energy. By colliding particles together, the kinetic energy will form new particles. We can do that. But every time you get a particle of matter, you get a particle of antimatter. Every time you get a proton, you get an antiproton. You get an electron, you get a positron. Okay, so the question then that I have is, where's the antimatter? Because if all the matter in the universe was produced from energy, it should have produced an equal amount of antimatter. But we don't see it. The universe is essentially matter only. It's like 99.999% matter. And any antimatter we produce is local. It's produced by high energy processes and then almost immediately destroyed by contact with matter. So that's a problem in the secular view. And there have been attempts to explain it. One of the earlier attempts predicted that a proton would decay after a certain amount of time, and that's now been refuted. Protons are stable, at least within the ability of our instruments to measure that. So that version's gone. But these various models to explain this, a lot of times what they'll do is they'll say, well, perhaps one time in like 100 quadrillion, the energy will produce matter only. So there's a asymmetry there. It's not been observed though. And so again, it's not part of science in terms of what we've been able to perceive in the present. What we observe is that every time you get matter, you get antimatter from energy. So that suggests to me that the universe was created by God. And he made it matter only as a design feature, because if he made it a mix, we wouldn't be here to have this conversation, because it would destroy itself. So it's a design feature. We find distant mature galaxies, and it's interesting too because they keep pushing this back. They used to think that when galaxies formed, in terms of how long it would take them to form after the Big Bang. It takes a while for gas to accumulate and for its gravity to pull it into these shapes. And yet, as far out as we see, you see galaxies. You don't see galaxies starting to form. You see galaxies, fully formed, fully designed galaxies. Some of them spirals. There's a lovely little spiral galaxy down there. Isn't that pretty? And this was astonishing when this was discovered to the secularists, that when we pointed the Hubble telescope out in the section of space that's relatively empty in our own galaxy, to see what's beyond, you see hundreds of billions of galaxies. It's wonderful. Unexpected, the Big Bang view. And we don't see galaxies starting to form. We see fully designed galaxies. And then we have the problem with population 3 stars. So stars like the Sun are called population 1 stars. They have a fair fraction of heavier elements. Remember those heavy things heavier than lithium. So the Sun has some carbon in it. It's got some oxygen in it. That's like 1%, right? It's mostly hydrogen and helium, but it has like 1% of these heavy things. Then there are population 2 stars that have very few heavy elements. Okay, it's like 10 times less heavy elements than the Sun has. Now, if the Big Bang were true, remember the Big Bang produces only hydrogen, helium, and trace amounts of lithium. If that's true, what should the first stars be made of that formed after the Big Bang? They should be made of hydrogen, helium, and trace amounts of lithium. That's it. They can't have the heavier elements, because those heavier elements are supposed to be produced in that first generation stars. So these first generation stars would be called population 3 stars. They should not have any heavy elements. And some of those stars should have lasted till now, because the red dwarf stars, for example, theoretically you calculate the amount of mass, you calculate the rate at which they're using up their energy, they should be able to last easily 13 billion years. So there should still be a lot of these around today, these population 3 stars. How many have we found? None. And that's astonishing, considering we have 100 billion stars in our own galaxy. We don't find any population 3 stars. You find some population 2 stars, you find some population 1 stars, but none of these original stars that were allegedly produced in the Big Bang. And it's pretty amazing, some of the stars that we find in our galaxy, but none of them are population 3. So, and these are, by the way, you'll find these in the secular literature. And my secular colleagues might say, well, I think we can work around some of these. Okay, but my point is they're there. These problems do exist. And so we've already seen that the standard cosmological model is not good science in the sense of testable, repeatable laboratory science. It can't be repeated in a laboratory. Critics say, oh, but creation can't be repeated either. Well, that's true. I never said creation was a scientific fact. Creation is an historical fact. It's recorded history. We don't have that with the Big Bang, however. It's not compatible with the Bible. And there's scientific evidence that challenges the standard cosmological model. And there are observations that are consistent with the young universe. And this takes a little bit of explanation, because a lot of times when we use these arguments for a young universe, people kind of misunderstand what we're doing. So I want to explain this a little bit. Creationists and secularists have different presuppositions which affect our estimates of age, because we have different assumptions about the past. We have different assumptions about how rates and processes have worked and what the initial conditions were and so on. So when we're debating about the age of something, how do we come to agreement on this? Those of you that are coming to the conference tomorrow will actually talk a bit more about how to deal with presuppositional conflicts and how to resolve those. But just to give you kind of whet your appetite here, those who hold to the biblical time scale, those who hold to the secular time scale have different presuppositions. Those who hold to the secular time scale tend to hold to uniformitarianism, which is the idea that rates and conditions today are basically representative of those in the past. And so a uniformitarianist would assume that since mountains grow at a very slow rate today, the Himalayan range is being pushed up very slowly today, that's always been the case. And so assuming that The mountains have always grown at that rate. We worked the calculation back. You say they're very, very old. They're millions of years old. In the biblical timescale, though, we believe in catastrophism. We believe that there has been a catastrophe, at least in Earth's history, worldwide flood. We think that the Bible says all the fountains, the great deep, burst forth. Maybe a reference to underwater volcanism, perhaps plate tectonics. We think a lot of stuff happened in Earth history at a rate that's much faster than what happens normally today. So we do believe in past catastrophes, and that the majority of Earth's main features were produced in those catastrophes, especially the worldwide flood. The secular time scale, those who hold to that tend to hold to naturalism, the belief that nature is all that there is, and that it happens needs to be explained by natural law. Now, as a biblical creationist, I believe in natural laws, but I believe God is not bound by them. And I believe the universe was not created according to natural laws. Because if you think about it, what a natural law is the way God normally upholds his creation. Isn't it? So people say, well, why do the planets orbit the sun? Well, gravity, right? So we don't need God, we just need gravity. Well, gravity is just the name we give to the way that God causes planets to orbit the sun. And the fact that we can write down nice neat little equations that describe the way that God upholds his universe tells us something about the mind of God. God thinks logically, he thinks mathematically. So natural law is not a replacement for God's power, it's an example of God's power. But at the same time, God is not required to do things. He's not required to create the universe in the same way he upholds it. And during the creation week, God was doing things that he's not doing today. He was speaking new things, new matter into existence during the creation week. Okay? He was creating new varieties of animals, or new kinds of animals. We do get diversification, of course, but God's not speaking new things into existence today like he did during the creation week. So I hold to a supernatural creation. And that will affect my age estimate, won't it? Because you see, if you hold to a secular time scale, and you say, well, everything has always been at the slow rate it is today, and God didn't create it, it came naturally. Well, it would take a long time for a planet like Earth to form by dust grains collecting. Therefore, the Earth's got to be really, really old. And it would take a long time for mountains to be pushed up and so on. And so that is the natural conclusion given those presuppositions. Looking at the evidence, that's what you conclude. However, if you start with biblical presuppositions, you say, well, there's been one or more catastrophes on Earth, especially the worldwide flood, and perhaps a lot of geologic activity during the creation week, as God was bringing the continents up from the oceans and so on. And frankly, the universe was spoken into existence by God, just like that. That doesn't take any time. So I'd say, creation a few days, 6 days, a few thousand years ago. Now, it would be ridiculous for me to say, assuming catastrophism, assuming supernaturalism, you get 6 days of creation. That proves it just by itself. Just as it would be ridiculous for the secularists to say, well, assuming uniformitarianism and naturalism, you get billions of years. Well, of course. The problem is not the evidence. The problem is which of these sets of presuppositions are right. It does no good for me to stand on my own presuppositions and say, well, I believe that comets are thousands of years old because at the rate they disintegrate and so on. But see, my secular colleague is going to look at that same evidence, but he's going to have different presuppositions. He's going to draw different conclusions. How can we get anywhere? And one of the things you can do, and I'll talk about this in more depth tomorrow, but one of the things we can do is an internal critique. And so what I do is I temporarily, for the sake of hypothesis, I'll assume the secular time scale. You see, an internal critique is the only way to resolve a worldview debate. So what I'm going to do is hypothetically assume the starting positions of my opponent. Not that I'm really accepting those. I'm merely accepting them for the sake of argument to show that they lead to a contradiction. So what I'm going to do is I'm going to say, okay, I'll grant it for the sake of argument. I don't really believe in uniformitarianism. I don't really believe in naturalism. But for the sake of argument, let's assume those are true. And we're going to find that there is some evidence that is still inconsistent with billions of years, even if you assume these presuppositions. Does that make sense? Because a lot of times these arguments, we'll use them and people say, well, you used uniformitarianism in your argument. You said you don't believe that. I know, I'm doing it for the sake of argument to show that even if you do assume it, you still get young ages. That's the point. I'm temporarily assuming the secular presuppositions to show that it leads to an inconsistency. And there are many examples of this. One is the recession rate of the moon. The moon is actually spiraling outward due to tidal forces. That confuses people because they think, well, gravity is attractive, right? Well, yes, it is, but gravity keeps the moon in orbit. But the moon induces tides on the Earth's oceans. It pulls on Earth's oceans. That pulls some of the water up. That creates two tidal bulges. The Earth rotates faster than the moon orbits, and so the tidal bulges are always getting ahead of the moon, and therefore they pull forward on it. And when you pull forward on something in orbit, it moves out. It's a little bit counterintuitive, but if you've ever played with a gyroscope, you know that the rumble is kind of the way your intuition is felt when something's spinning. And so, in the same way, when the astronauts want to go to a higher orbit, they thrust forward, and they'll put them into a higher orbit, because the moon's gaining energy, stealing a little bit of energy from the Earth to move outward. And today that rate is about 1.5 inches a year. We can measure that. We left reflectors on the moon. When the astronauts were there, we can bounce a laser off of them, get the time, divide by the distance, and get, using the speed of light, and we can get the distance to the moon within a fraction of an inch. And it is spiraling away from the Earth. We'd expect that. That means if you run the movie backwards, well, in the past, they would have been much closer, right? And you have to do the math properly, because the rate, we would expect it to change a bit, because as the moon is closer to the Earth, the tidal bulges would be bigger, and that would cause the moon to move even faster, right? So running the movie backwards, it gets faster and faster and faster. You do the math right, and you find that the Earth and the moon would collide in less than 1.5 billion years. You say, well, that's a long time, 1.5 billion years. Yes, it is. But the Earth and the moon are supposed to be 4.5 billion years old in the secular view, right? And 1.5 is less than 4.5, right? Even the common core folks get that. Okay. So again, I'm using the secular assumptions of uniformitarianism. I'm assuming that the tidal braking constant's always been the same. The rate does change. We'd expect that on the basis of physics, but I'm assuming the tidal braking constant's uniform. And you get a collision. It's inconsistent with the secular view, isn't it? Now, they could save themselves by saying, well, the tidal braking constant's not constant. But then what are they giving up? Uniformitarianism. The very thing on which they base the things years. Spiral galaxy winding. We've been able to measure the velocities in these stars as the galaxy rotates. We can measure their Doppler shift. It might look like this galaxy's face on. It's actually slightly tilted. And we get a Doppler shift of the stars that's been measured by astronomers. And you'll notice that these stars have a linear profile here. They're kind of straight. They all have the same velocity. That's the same linear velocity, which means their angular velocity drops. What that means is the inner portions of this galaxy wrap faster than the outer portions. The same reason, if you have two guys on the track and one guy's on the inside, the other guy's on the outside, even if they're running at the same speed, the guy on the inside is going to win, isn't he? Because he's got the smaller circumference, right? It's the same way with the galaxy, that the linear speeds are about the same, and therefore a galaxy will wrap itself up. And so I was curious, how long does it take a galaxy to wrap itself up? How long does it take before it's twisted beyond recognition? And so I took the measured velocities of those stars, I wrote a computer simulation to see what happens to a spiral galaxy over millions of years. And I ran the simulation out to 100 million years. Now, by the way, my secular colleagues believe spiral galaxies are 10 billion years old. I only ran the simulation out to 100 million years because at that point it starts looking like an old-fashioned phonograph record. It doesn't look anything like the spiral galaxies we see in the actual universe. I've seen a lot of galaxies in my telescope. I've never seen one that looks like that. And that doesn't even go out to 1 billion years. They're supposed to be 10 billion years old. I didn't even run out to 1 billion. I ran it out to 100 million. And it's totally twisted beyond recognition. So, and my secular colleagues are aware of this. It's the spiral wrapping problem. We covered this in grad school. And one of the solutions is, well, yeah, there's no doubt the spiral lines wrap quickly, so there must be a way to make new ones. And one of those ideas is called the density wave hypothesis. And the idea is that there are these waves, compression waves, that go around the galaxy forming, they trigger new star formation, and that creates new spiral arms. But I think there's a huge problem with that. You see, magnetic fields, these galaxies have magnetic fields, and magnetic fields do not move with density waves. Magnetic fields move with material, because plasma can't move across a magnetic field line. That's a principle of physics. And so the bottom line is the magnetic fields would cancel out. If these galaxies had wrapped around themselves many times and the new spiral arms had formed, the magnetic field should be gone. It should have canceled itself out. But in fact, we've been able to measure the magnetic fields of these galaxies, and the magnetic fields trace with the spiral arms, which means those spiral arms, they haven't wrapped around themselves many times and then been recreated, because the magnetic fields would not be lined up that way. So the bottom line is, if the universe is a few thousand years old, 6,000 years old, you expect to find spiral galaxies. They haven't wrapped very much in 6,000 years. I think God made them already spirals. They've wrapped a little bit since creation. If they were even 1 billion years old, they'd look like that. That's the simulation out to 1 billion years. What kind of galaxies do we observe? Ones that look like they're about 6,000 years old. I mean, it's interesting to me, because some people will say, but Lisle, if the Bible's true, if the universe is really young, why does it look so old? And I'm thinking, I don't know what universe you're looking at, but the one I look at looks very young. It looks thousands of years old. The internal heat of the Jovian planets, Jupiter gives off more than twice as much energy as it receives from the sun. So does Neptune. Neptune gives off 2.6 times, 2.6, 2.7 times as much energy as it receives from the sun every second, taking in 1 unit, giving up 2. Can't do that forever. It's going to lose it. It's constantly losing energy, right? And you do the math. Jupiter and all the other planets they should have lost all their heat by now. Because they're not, I mean, Jupiter's 10 times the size of the Earth, and it can maintain heat for millions of years potentially, but not 4.5 billion. It should have run down by now. The problem is even worse for Neptune. Neptune's only 4 times the size of the Earth, and it has more internal heat than Jupiter does. And so, if it were, 6,000 years old, it's not a problem. It hasn't run out of heat yet. In 6,000 years, it's cooled off a little bit, but not much. And so the temperature of, I guess that's Neptune, is 72 kelvins at the surface. It should be 58 kelvins at the surface if it were billions of years old. It should have run out of internal heat. That would be the equilibrium temperature at that distance. And yet we find that it's consistent with the biblical timescale. The rate at which Earth's magnetic field decays appears to be an exponential decay. We've been able to measure it for the last almost 2 centuries, and it's dropping. We can measure that. The exponential decay has a half-life of 1,400 years. Some estimates put it even less than that, but I'm being generous to the critics. And so you find that the magnetic field would have been 20 times stronger at creation 6,000 years ago. But you run it back, again, assuming naturalism, assuming uniformitarianism, just assuming that rates are basically constant, and you run it back, and you find that 50,000 years ago, the magnetic field would have been 56 billion times stronger than it is today, which is enough to rip the iron out of your blood, so you don't want that. And that's not millions of years, that's 50,000 years. That's a tight constraint on the age of the Earth, just based on the magnetic field. And again, my secular colleagues say, well, the magnetic field is flipping and it recharges itself, but the evidence is just consistent with an exponential decay. Therefore, that would be the uniformitarian assumption that it's always been that way. And it's not just Earth, the other planets of the solar system, at least some of them have magnetic fields. Jupiter's is enormously powerful. And we have a spacecraft orbiting very close to Jupiter, closer than any other has orbited. And they had to design it specially to protect it from the radiation that's induced when you move electronics through a magnetic field like that. And pretty amazing. But magnetic fields just don't last billions of years. Uranus and Neptune, magnetic fields, they're consistent with thousands of years. A friend of mine, Russ Humphreys, who's a creation physicist, he actually predicted the magnetic fields of Uranus and Neptune before they were measured by the Voyager 2 spacecraft. He predicted them back in 1984. He predicted that the magnetic field strength of the planet Uranus should be that number. It should be that blue bar at the top. That's the range. And it's a logarithmic plot, so it's a little more range than it probably looks. But in the secular view, the magnetic field should be essentially gone. Right? It shouldn't be a magnetic field, at least not a measurable one, after billions of years. And when Voyager 2 flew past, it measured the magnetic field at that level. Isn't that interesting? And it's just spot on with what Humphreys had predicted. And likewise with Neptune, he was right on that as well. In fact, his model can explain the magnetic field of any planet. It's just that it's neat for Uranus and Neptune because they hadn't been measured yet when he came up with his model. So those two are predictions, and pretty neat. So comets are made up of icy material that's constantly being depleted as they come close to the sun. So comets spend most of their time away from the sun, and they'll come close, and that icy material gets blasted away. And so every time you see a comet, it's getting smaller. That's what the tail is. The tail is material that's being drained away from the nucleus of the comet. And so we estimate a typical comet could last no more than about 100,000 years. And some of them are very quick, because I use the SOHO spacecraft in my doctoral research, and it has an instrument on it that's designed to block the sun and see things that are very close to the sun. And a lot of times comets get really bright when they get close to the sun. They're hard to see in our sky because the sun's up, it's daytime. But SOHO is designed to do that. I've seen comets that have gone behind the sun, and that's it. Totally destroyed. I've seen a number of comets that no longer exist. So my point is they don't last billions of years. And my secular colleagues are aware of that. And so they say, well, there must be an Oort cloud that makes new ones. I've heard the Oort cloud. I'll talk about this more tomorrow when we talk about rescuing devices. But and in my view, this is kind of like the epicycles that Ptolemy added to his model to make it work. The idea is that there's a comet generator that makes new comets as the old ones are depleted. We'll talk more about that tomorrow. But the bottom line is, comets really are consistent with a young solar system. And if it were billions of years old, you should not see comets. They shouldn't be there, and yet we do see comets. So again, the evidence seems to be consistent. Even assuming the secularists' assumptions of uniformitarianism and naturalism. Blue stars are the hottest stars in the universe. They're the most massive, and they can't last millions of years because they use up their energy at an alarming rate. The energy of a star, its fuel is itself. It uses its own hydrogen gas to power it, hydrogen fusion in the core. And although blue stars are the most massive, they have the most fuel available, they use it up at an alarming rate. They're kind of like the SUV of the star world. They have a big gas tank, but they get very poor gas mileage, and so they can't last very long in time. And so, it's a problem. And my secular colleagues are aware of this. And as far as I know, I don't know anyone that even disputes that blue stars can't last billions of years. So they'll say, well, obviously they formed recently. If you see a blue star, it must have formed recently. It's probably in a star-forming region. But no one's ever seen that. There are theoretical problems getting a star to form. And again, I'll grant, a star is not an organism. Perhaps they can form. It's not like a complex machine, like a living organism. They're a ball of gas. But it is really hard to get gas to just collapse in on itself, because gas has a tendency to expand. You know that. You didn't hold your breath when you came into the room in case all the air was in the corner. You expected it to then spread out, because that's what air does. That's what gas does. Gas pressure. And theoretically, you can have a condition where the temperature is so low that the gas pressure is minimal, because the hotter the gas is, the more pressure it has. Theoretically, you can have a state where the gravity is more than the inward force of gravity outdoes the gas pressure, but we haven't seen that except for stars that already exist. Once you have a star, because it's in such a small space, its gravity will keep the gas from expanding. But to get it to that state is problematic. And then you got to figure out how to dump the angular momentum, because nebulae, they have a little bit of rotation to them. And if you compress it down, it's like a skater when she pulls her arms in, speeds up, and that tends to prevent further collapse. So you have to dump the angular momentum somehow. There's magnetic fields that trace these nebulae, and what happens when you push a magnetic field together? What happens when you push a magnet north to north, right? They repel, right? So it wants to prevent further collapse. So there's all kinds of problems with star formation. It's not something that's been observed, and it has theoretical problems as well. So really, if the universe were 6,000 years old, you'd expect to have blue stars and red stars. Red stars can last a long time, so they exist in both a young universe and a theoretical old universe. But in the old universe, you shouldn't have any of the blue stars. What do we find? Lots of blue stars, especially in spiral galaxies. Spiral galaxies in the spiral arms can have a higher proportion of blue stars than the core. So lots of evidence for a young universe. But what about distant starlight? I want to hit that briefly, because I think that's an issue that comes up from time to time. And I haven't come up with a good way I think we have a good solution to that. I just haven't come up with a good way of explaining it. But I'm going to try something. We'll see if it works. So we have here an example of this is a space-time diagram. So the Earth in the center, that's right here, right now. And then the x-axis, that represents space. So this is far away over here, far away from the Earth. Let's say this is the north side of the universe, and that's the south side of the universe. Then we can only do one dimension of space, because the other dimension is only used to represent time. And so that axis represents time. So those points are far away. That represents the future, that represents the past. And just by convention, we put the future up. I guess we like that. And so x, and then t, you multiply it by c, so the units are the same. Because we measure distance in things like meters, but we measure time in things like seconds. That's kind of inconvenient. So if you multiply it by the speed of light, you can measure both in meters, and so the units are the same. That's why we do that. So if you think about, so we have these galaxies that are far away, and the question is, how does light get here? Well, let's think about how light works. If I were to, this is right now, if I were to take a light bulb and turn it on for just an instant, the light would move away from the Earth, like that. Okay, and that's the way it's normally illustrated in textbooks. And if you do it this way, the way Einstein did it, it will travel out at sort of 45-degree angles. Light will move 1 unit in space as it moves 1 unit in time if you use those units, multiplying by c. Okay, so that's light that I create right now. I emit it from the Earth and it travels away. And we call that a light cone. Because if you were to add another dimension out this way, the light would form a cone. And in all 3 dimensions, it forms a hypercone, which we can't quite picture because we can't think 4th dimensionally, really. So that's how light's represented. And light that's that we're just seeing right now would be represented by that. So any star that I go out and I look and say, and I see that star, the light from that star is represented by one of those two beams. Okay, if it's on the north side of the universe, that's the beam. If it's on the south side, that's the beam, and so on. Okay, so now normally we would say, well, there's a question of how do we define now? And when you're on the Earth, you're right here, you say, well, now is right now. I know the time, that's easy. But how do we define now for something that's far away? Future is obvious, that's vertical up there. It's within that light cone. Past is within that light cone. Those are easy. How do you define now? Normally the way we define it is we say, well, it's the axis that's perpendicular, so that these represent points right now far away. Make sense? That's the way most physicists do it today. Turns out you don't have to do it that way, but that's the way most people do it. And so if you think about a galaxy as it is right now, a galaxy now that's far, far away would be that one, right? A galaxy that's in the distant future, that's far, far away, would be up there. And a long time ago, a galaxy far, far away would be right there, right? So that's when Star Wars happened. So here's the problem then. Here's the problem, the perceived problem. Because there are galaxies that are billions of light years away. They're very far away. And light will travel 1 light year in a time of 1 year. That's why it's the 45-degree angle. And so if I'm seeing this galaxy now, the light must have been emitted in the distant past. You see, it must have been emitted billions of years ago in order for me to see it now, but the Bible's not true. That's the thinking. Well, until Einstein comes along and realizes space and time don't work exactly the same way people think. One of the things Einstein talked about is an observer that is in motion relative to another observer. If there's an observer, we're still here on Earth, but suppose there's a spaceship traveling right by the Earth right now. And so his line would be represented like that, right? Because he's moving, let's say he's moving from there to there, and he's doing that as a function of time. So in the past, he was in this position in space, and in the future, so in the past, he's on the left side of the Earth, the future is on the right side of the Earth, because he's moving. And so that's what his path would look like. That's what his path would look like on the space-time diagram. And if you think about it, that's his time axis. Because from his point of view, and he's in the rocket, his engines are turned off, he's coasting past the Earth, so as far as he's concerned, he's stationary, and he's seeing the Earth move the other way past him. And so since he's stationary, he sees that as his time axis. We'll call that T prime. That's his future. See, in the future, he's to the right side of the Earth, or the Earth is to the left of him. And the interesting thing is, his x-axis would be this. And that's something that, I'm not going to go into why that is, but I do have a book on the topic if you want to learn how that is. That's his x-axis. Okay? And so the interesting thing is, if that's his x-axis, and we're defining now as being along the x-axis, then that means that's his definition of now. Interesting. Using the same rules that I'm using, forming the light cones, and assuming that the x-axis is perpendicular to the t-axis, that would be his definition of now, even though that's our definition of now. And I'm talking about as he passes the Earth. So right now, let's say an explosion happens out here, and God tells us about it, because we can't see the light yet. So God whispers in our ear and says, okay, there's an explosion right there. From his point of view, it happened a long time ago. It's in his past. Isn't that interesting? This is called the relativity of simultaneity. It's something that Einstein discussed in his book. It's a fascinating topic. It's weird. I know it is, but it's true. And you say, but wait a minute, his time axis and his space axis are not perpendicular. But to him, they are. Because to him, the situation looks like this. Okay? So this object down here that God has whispered in our ear and told us it just happened, he would say, well, that happened for me, that happened a long time ago. Okay? And conversely, things that are in his past, depending on where he's at, they could be in our future, and his future could be in our past. It's really strange. Is there anything we can agree on? And the answer is yes. The light cones. We agree on the light cones. You notice those didn't change? Let me go back. See, look at the light cones. They remain unchanged. Because one of the principles of relativity is that the speed of light's constant regardless of your motion. And so we can agree, and we can agree on the future. We all agree that the future is contained within that light cone. Both the moving observer and the stationary observers on Earth say that's the future. Both the moving observer and the stationary observers on the Earth agree that this is the past, everything within that light cone. But in terms of what is happening now, out here, it's up for grabs. It depends on your state of motion. Now, is there a convention we could use? Normally the convention is we pick it to be perpendicular, such that the light axes are 45-degree angles, and we just define that to be now, and we just live with the fact that other observers will disagree on what represents now at a distant point in space. We just live with the inconsistency. Is there a way we could define now at a distance to where both the moving observer and the stationary observers will agree? And the answer is yes, we can. If you make the now axis match with the past light cone, like that, then everyone would agree, this is now what I'm defining as now. And you say, but I don't like that, because it looks like it's in the past, but that's no problem, because we can regraph it like that. Okay? That's fine. And so there you go. And the interesting thing is, if we use this, first of all, there's no starlight problem, because this is the past light cone, isn't it? And so if the star explodes right now, we see it right now. We see it immediately, if we use that convention. And the part that people really have trouble understanding is that I'm not saying the other convention's wrong. It's just different. It's just different. Because people think, well, one of the two has got to be the right definition of now. What I pointed out to you is that according to Einstein, there isn't a right definition of now at a distance. There's just different conventions of what we decide. And it turns out that all ancient cultures actually use this convention. It wasn't until really the 20th century that people started using the other, the light cones and such. So this is what we would call an anisotropic synchrony convention, because the speed of light, it looks like it's a different speed going in than it is out. It looks like it's infinitely fast coming toward us, and then it travels at half speed when it's leaving us. And that's fine, but that's just the weirdness of the universe that God has made. We can define time in that way. So, and again, I'm thinking of different ways to explain this. I hope that makes some degree of sense. But the point is, there are different definitions of what constitutes now in deep space. And if you use this one, you're seeing the universe in real time, even today, and there's no starlight problem. And I think the Bible suggests that convention. For one thing, when God makes the lights in the firmament, it says, let them be for signs these days and years, the stars also, and let them be for lights in the firmament of the heavens to give light upon the earth, and it was so, indicating that God made the lights and they immediately gave light on the earth. And so that would suggest that God was using that convention, which again, all ancient cultures did. They did not subtract off light travel time. When you see something happen, so that's how you define now. Isn't that intuitive? If you see a deer across the hill grazing over there, and you say, wow, I wonder how many millions of years ago that happened. It doesn't even occur to us, right? We think, well, that's the way it is now. And if you use this convention, that works even out in space. You're seeing things as they are now, because that's the way we're defining it now. And that turns out that's consistent with all known physics. Physicist John Linney in 1970 showed that all relativity works under this coordinate system just as it does in the other coordinate system. So there's no starlight problem. There really isn't. There never has been. It's just we've been using the wrong synchrony convention. So observations really are consistent with the young universe, even distant starlight. There's just not a lot of people know about the physics of Einstein, which is why I wrote a book on it. And then I want to show you that biblical creation is the foundation of science. And this is powerful. And I'll cover this more tomorrow, more in detail. But I want to give you kind of a preview of it this evening. And some of you can't come back tomorrow, so that's fine. So biblical creation is actually a prerequisite for science, because in order for science to work, the universe would have to be a certain way. And we have to know that the universe is that way. And the only way that you can know that the universe is the way that is necessary for science is if God tells you that, and He has, in the Bible. We would expect that the universe is logical and orderly because it is upheld by the mind of God. God is logical and orderly. He's imposed order in the universe. We expect to find patterns in nature. And that's what science is. It's about finding patterns in nature. And you wouldn't expect that if it was just a chance universe. Why would you expect to find patterns in an accident? Something that's not generated by the mind. Why would there be any logic to it whatsoever? Logic is an aspect of thinking. It's an aspect of rationality. Why would we expect to find rationality in a chance universe that's not controlled by a rational mind? So if science is possible, then biblical creation must be true. That's a different kind of an argument, and it's powerful. I had some students today. I spoke at a Christian school, and there were actually some non-Christians there, and they came up to me afterwards and were peppering me with questions, which I love. I was happy to answer those. And then I challenged them, because he said, one of the guys says, I don't believe in the Bible. I asked him, do you believe in the Bible? No, I believe in science. And so when you realize that science is predicated on Christian worldview, that took him by surprise. I didn't realize that. But I want to give you an example of this. One example of what we might call a prerequisite for science, something that the universe has to be a certain way for science to be possible, is there has to be a degree of orderliness or uniformity in nature. And please don't confuse this with uniformitarianism. I don't believe that rates and conditions are always constant, but I do believe there's orderliness in nature, that there's a uniformity to it. And what we might characterize as laws of nature that don't arbitrarily change with time. No, God can, but He doesn't normally. And normally He upholds things in a consistent way for our benefit. All technology is based on that principle, right? It assumes that the patterns of nature will continue in the future as they have in the past. The laws of nature are consistent over time and space. All astronomers assume that physics works the same way in and around the galaxy as it works here on Earth. I've never met anyone who believed otherwise. You couldn't do astronomy without that assumption. And in the Christian worldview, that assumption is justified. It's not just an assumption. It's what we expect. Because God is sovereign over the around the galaxy, just as He's sovereign over the Earth. He's omnipresent. He upholds the entire universe in a consistent way. So the fact that what works here will work over there if the conditions are similar, you get a similar result. Likewise, the future and the past work the same way. If I do an experiment on Monday and get a certain result, I expect that if I do the same experiment under the same conditions on Tuesday, I'll get the same result. That's a Christian presupposition, folks. How could you possibly know that apart from the Christian worldview? And it won't do to say, well, it's always worked that way, because then you're assuming the very thing you're trying to prove, that the future will be like the past in terms of general principles. But in the Christian worldview, we have a promise from God that those basic cycles of nature will be in the future as they have been in the past, as long as the earth remains. After the flood, God promised, while the earth remains, seed time and harvest, cold and heat, winter and summer, day and night shall not cease. It's referring to the seasons, the cycle of the seasons, referring to the day and night cycle. It's referring to these cycles of nature. We've discovered other ones since then, right? We've discovered other cycles of nature, on the quantum scale, the way the atoms vibrate and so on. We expect that will continue to work in the future as it has in the past. And only God's in a position to tell us that on His own authority, right? Because He's beyond time, so He knows the future. He's omniscient, He knows everything. And so He's in a position to tell us that. But the Big Bang supporter has no basis for uniformity of nature. Oh, he assumes it. Everybody does. You couldn't get out of bed in the morning without that, because you assume that gravity will work the same way as it did yesterday. You assume that momentum will work the same way as it did yesterday. You couldn't walk without that assumption. But they don't have any basis for it on their own professed worldview. Every step you take presupposes uniformity in nature. And that makes no sense to believe in that in a chance universe. Let me give you an example. Suppose you get up in the middle of the night to get a drink of water and it's very dark, and you're stumbling around and you stub your toe on something. Ah, that hurts. Now the next time you get up to get a drink of water, you say, I'm not going to stub my toe this time. I'm going to think it really clear. I'm going to turn the lights on this time. I do not want to stub my toe again. Why? Because you assume that if you stub your toe again, it will hurt again. Now in the Christian worldview, you have a very good reason for that. God's told you He holds the universe in a consistent way, that there are these cycles that will continue. You stub your toe again, it's going to hurt again. But in a chance universe, why would you assume that? It's a chance universe. Maybe the next time I stub my toe, it'll be the most enjoyable experience of my life. Yes, we can know something about the future because God's told us that. So we know the patterns will continue in the future. That's why we can predict the positions of the planets. I've written software myself that can predict the positions of the planets 1,000 years in the future should the Lord tarry. Because God's promise, as long as the earth remains, you're going to have that uniformity. So I can do that. Now everybody believes it. Everybody believes the sun's going to rise tomorrow. But only the Christian, the consistent Christian, has a logical reason for it. And it won't do, I'm going to go through some of these tomorrow, but it won't do to say, well, the reason I believe the sun will rise tomorrow is because it always has in the past. Because that assumes the very point I'm trying to get you to justify. You see, whenever we use past experience as a basis for what is likely to happen in the future, we're assuming uniformity. So you can say, well, because this happened in the past, very probably it'll work in the future. I'm assuming Uniformity. Now, if I ask you, how do you know there's going to be uniformity? You can say, well, in the past there was uniformity, therefore in the future there will be a uniformity. What are you assuming? Uniformity. Let me try to break this down for you, because I know it's hard. We assume uniformity. So it's so basic to us that when we try to defend it, we assume it while defending it. And that's a circular reasoning, and we'll talk about that tomorrow too. But you see, when the person says, well, the reason I know the sun will rise tomorrow is because it always has. You see, in the past, there was uniformity. In the past, futures were like the past. Past futures were like past pasts, right? And we know that now because that's now all in our past, and we can remember it. Okay, I'll grant you that. Therefore, in the future will be like the past. Future futures will be like future past. But he says, therefore, what's he assuming? The future will be like the past. Which is the very question I'm asking him to justify. And by the way, make sure you understand that, because you will be asked to explain that at some point. It is so basic to us to assume that the future will be like the past. We don't realize that is a Christian presupposition that cannot be justified apart from the Christian worldview. You don't believe me? Read David Hume. David Hume, the secular philosopher, was stumped on that question. He was very frustrated that he knew the sun would rise tomorrow, but he could not come up with a non-Christian explanation as to how he knew that. Frustrated him to the point he said, I'd rather just give up philosophy and go play games with my friends. Interesting. And again, I'll go into this more detail tomorrow. You can see how it really is very powerful when you realize that science only works because the Christian worldview is true, which may explain why many of the founding fathers of science were consistent Christians. So, we've seen that Christians should reject the standard cosmological model for a number of reasons. It's not good science, which by itself isn't a reason to object to it. It's just I'm getting really tired of people saying, well, this is the scientific position. Excuse me, none of the 7 steps are scientific. They're not. I'd rather you say, this is a story about the past that we believe. Okay, now we can talk. But it's not compatible with the Bible. I've got a story about the past too, but mine is recorded history. It was recorded by eyewitnesses and has the approval of Almighty God. Yeah. There are scientific evidences that challenge the standard cosmological model. And I didn't invent any of these. These are all in the standard literature. You can look them up in the standard textbooks. Some of them, they think they've solved, others are not. The baryon asymmetry problem has not been solved. Observations are consistent with the young universe. Even if you make the secular assumptions, you still get young universe answers in many cases, which is an example of an internal critique. And then we've seen that biblical creation is the foundation of science. It's what makes science possible. And again, we'll go over that more tomorrow as well. That's very powerful, because when I was chatting with these youngsters today, and they couldn't get around that one. And nobody can. Nobody can. If you'd like to learn more about these topics, we have a number of resources at our table back there. If you want to learn more about the distant starlight issue, I've written a book called The Physics of Einstein, and it's exactly what the title implies. It's going to teach you the physics of Einstein, which is not nearly as hard as people think it is. It's actually I think it's different. It's a different way of thinking. But I wrote this book for laymen, so you don't need to have any background in science to understand this. Now, I did put in-depth boxes for those who appreciate math and science and want to go into more detail, but you can skip those and it's still very readable. And so you can do it either way. One of the neat things about the physics of Einstein is most of it's provable, which is rare in science. In science, most things are done by induction. We draw inferences from general patterns, but not so with physics of Einstein. Most of it is logically provable. Taking back astronomy, if you want to see some of these evidences that are consistent with the young universe, that's a powerful resource that I encourage you to get. And how the universe is consistent with creation, biblical creation, not a Big Bang. We have a DVD along those lines as well, Astronomy Reveals Creation. What about the days of creation? Can we really know those are ordinary days? Well, yes, you can. There's the book on the topic, Understanding Genesis. Is there one right interpretation of the Bible, or are there many? We're just going to help you through that, and maybe to help you with Christians who say, well, you know, I'm a Christian, but I don't read the Bible the same way you do. Well, let's chat about that, because the Bible tells us how to interpret it, interestingly. A Stargazer's Guide to the Night Sky, How to Better Enjoy the Night Sky from a Christian Perspective. That's just a fun book if you want to learn about the constellations and things like that. And there's a gospel message in the back. I always like to include that, but it's mainly just a book to help better how to enjoy the night sky. And when's the next meteor shower, and things like that. That'll all be in there. Keeping Faith in the Age of Reason answers 420 alleged Bible contradictions. You hear the critics say, well, there's all these, how do you believe the Bible? This verse contradicts that one. I looked them all up. Not one of them was a legitimate contradiction. I'm just going to show you why. It's just kind of fun to go through those. And ultimate proof of creation, I'll talk about that tomorrow. I want to give you a bulletproof argument for biblical creation, so that's what we'll discuss at the conference, but we have the book on it. And discerning truth, spotting logical fallacies and arguments that evolutionists tend to make. And I just actually wrote recently a curriculum on logic. I'm really excited about this. And so we now have this available. If you want to study logic, you get better at it. It's a great resource for you. Logic comes from the Christian worldview. And that's a neat way to learn about it. We have a teacher's guide as well, if you want to use that as, with your students, or if you just want to get better on it yourself. You can get all the DVDs together for a discount if you want. You can get all the books together for a discount. You can get all the books and DVDs for an even larger discount. They'll probably put me out of business, but that's okay. We want to get this stuff in your hands. We have a free monthly newsletter, so be sure to sign up for that. It's an electronic newsletter. You'll get it in your email. So make sure you put your email address or you'll get nothing. Okay? We might make a paper version at some point, but in case for now, it's just email. It is free. There's no catch. Not too many things free in this world, just salvation and our newsletter. So make sure you sign up. And then check us out on the web as well at biblicalscienceinstitute.com. Do we do Q&A or are we done or what?
What I'd like to do, can you hear me? Yeah.
No.
No? No? No?
That might be a bid.
Yeah. Okay, so what I'd like to do, since we're running a bit over time here, is I'd like to go ahead and finish out the meeting. I have a few announcements that I need to tell you about for tomorrow and the next day. And then, if Dr. Lisle, if you're okay with that, can we take questions after that for those who would like to stay? Okay, let's do that. Everything seems to be acting up here for me. Oh.